Hi, welcome to your Mac 200 Statics online classes. Today we're going to cover the last part of Chapter 6 of the textbook, in which we have been learning how to analyze engineering structures using the equations of equilibrium. I hope you enjoyed this video. In the previous video, we've learned how to run structural analysis in a truss using the method of joints. Despite its simplicity, the application of this method for large and complex structures can be cumbersome, since it involves the application of the equilibrium equations for all joints in the truss. However, truss analysis using this method can be greatly simplified if we first identify the zero-force members. In other words, the truss members which support no loading. These zero-force members are used to increase the stability of the truss during construction and to provide added support if the loading is changed. There are some inspection rules we can apply to find the zero-force members of the truss. For example, let's consider the truss shown here. If we draw the free body diagram for joint A and apply the equations of equilibrium for the forces in the x and y directions, we easily see that the forces coming from members AB and AF are zero, and therefore these are zero-force members. Now let's take the free body diagram for joint D. Likewise, the application of the equations of equilibrium will lead to forces coming from members DC and DE being equal to zero, which makes them zero-force members as well. In fact, if a member is a zero-force member, it means that it has no participation in the transmission of the forces through the structure, and they can be eliminated, just for the sake of simplification of the truss analysis using the method of joints. From these observations, we can conclude that if only two non-collinear members form a truss joint and no external load or support reaction is applied to that joint, the two members must be zero-force members. But we have to be careful and state that these members must be zero-force members only for that particular loading condition. If the direction of the external load is changed or additional loads are added in any other joints, then these members might not be zero-force members. Now, let's consider another truss like the one shown in this video. If we take the free body diagram for joint C and solve the equilibrium equations for the x and y directions, we'll see that FCA is equals to 0 and FCB is equals to FCD. This means that member CA is a zero-force member and can be eliminated from the structure. If we repeat the process for joint D, we have that FDC is equals to FDE, FDA is equals to 0, and then member DA is also zero-force member, which can also be eliminated from the structure for the analysis. The resulting simplified structure will look like this one here. In general, if three members form a truss joint for which two of the members are collinear, the third member is a zero-force member only if no external force or support reaction has a component that acts along this member. Just like in the previous example, there is no guarantee that members CA and DA will remain as zero-force members if the direction of P changes, or if additional external forces are added to other joints of the truss. Now, we are going to learn a different method to perform truss analysis, which is called the method of sections. This method is based on the principle that if the truss is in equilibrium, then any segment of the truss is also in equilibrium. Unlike the method of joints, this method can be used when we are interested in finding the forces acting only a few members of the truss. For example, If we have a member of the truss subjected to a tension force, then if we cut an imaginary section of this member represented by a blue line, the two parts will also be subjected to tension forces as a result of the internal tensile forces propagated along the entire length of the member. Likewise, if we have a member subjected to a compressive force and an imaginary section line is passed through this member, the internal compressive forces acting along the member will determine the compressive state of the two resulting sections. This sectioning procedure applied to several elements of the truss is the basic idea behind the method of sections. However, the application of the equilibrium equations through this method is limited to the calculation of the unknown forces acting in maximum 3 members per sectioning. This limitation should define the strategy to minimize the total number of sections in the truss. In order to best explain how this method works, let's consider the truss shown in this picture, subjected to a 1000 newtons load applied at joint A. In this truss, let's say that we are interested in knowing the forces acting in members BC, GC, and GF only. Then, let's draw a section line AA passing through the 3 members of interest, in such a way that we split the truss into 2 sections, section 1 and section 2. After sectioning the truss, we have to indicate the forces acting on the 3 members of interest in both sections. Remember that whatever assumption we take for the known members, if they are in tension or compression, it must be consistent in the 2 sections. Here, we are just assuming that members BC and GC are in tension, whereas member GF is in compression. And we'll check if this assumption is correct after the calculations. Then, the first step for the solution of the problem is the calculation of the reaction forces at the supports following the usual procedure considering the entire truss. It's very important that we consider the entire truss for this calculation rather than the 2 sections separately. By simple inspection, we know that the 2 supports will develop 3 reaction forces, which we have to calculate using the 3 equilibrium equations. Let's start with the sum of the moments about joint D. By taking the 2 forces that generate a moment about this joint, we find out that the reaction force EX is equal to 3000 newtons. Next, taking the equation for the sum of the forces in the x direction, the reaction force dx can be determined as 3000 newtons as well. Finally, taking the sum of the forces in the y direction, the result for dy is 1000 newtons. All of them are positive numbers, which means that the assumption taken for the direction of the 3 forces in the free body diagram are correct. After the calculation of the reaction forces, the next step is to apply the same equilibrium equations at both sections to find the unknown forces acting on the 3 members of interest. However, when applying the equilibrium equations, we should carefully consider ways of writing the equations so that it yields a direct solution of the unknowns, rather than having to solve simultaneous equations. For example, using section 1, we can virtually extend members BC and GF to joint C, and write the equation for equilibrium of the moments about C. This is a good idea because only the 1000 newtons force and FGF will generate moments about this joint, and FGF is the only unknown, which can be solved directly. The calculated result for this force is then positive 2000 newtons. Since this is a positive number, it means that the sense of FGF assumed in the free body diagram is correct, and therefore it's a compressive force acting on member GF. We've got one of the unknowns of the problem. Then, let's check mark it in the free body diagram of both sections. Now, if we consider section 2, for example, and virtually extend members BC and GF to joint G, we can take the equilibrium of the moments about this joint. For this case, only the reaction forces at support D and the unknown force FBC will generate moments about this joint. Then the equilibrium equation can be solved directly to calculate the value of FBC, which is equal to positive 1000 newtons. This confirms the assumption that FBC is a tensile force, and then we check mark it on both free body diagrams. For the last unknown, which is FGC, we can go back to section 1 and perform the equilibrium analysis on this section, simply because it looks less busy than section 2 and easier to handle. It's convenient to take the equilibrium equation for the forces in the y direction, because we can write the vertical component of FGC in terms of the sine of the 45 degrees angle, which is counterbalanced by the 1000 newtons external force. By solving the equation directly, we can find that FGC is nearly 1400 newtons, and the positive sign confirms the assumption that FGC is a tension force. Then, the forces in all the three members of interest are determined. Now, let's discuss the pros and cons of the method of sections. Starting with the pros, the main advantage of this method is that there is no need to calculate the forces in all members. That's an important advantage if we compare it with the method of joints, in which we necessarily have to calculate the forces in all members first and look at the members of interest later. Another important advantage of this method is the ability to determine directly the force in a particular truss member by carefully selecting the section to be used and the joints about which the equilibrium equations for the moments will be applied. This advantage facilitates a lot the math to get the answers compared to the method of joints. For the cons, we can highlight that this method is limited to the calculation of maximum 3 unknowns per section. If we have to determine the forces in more than 3 members, more sections are required, which can make the solution process a little bit more complicated. Another drawback of the method of sections is that it requires some strategic thinking for the application of the equilibrium equations that will lead us to direct solutions for the unknown forces. For relatively simple cases, that should not be a problem. However, for complex stresses, the definition of this strategy might not be so obvious, which requires intellectual work. Now you are ready to study example 6.5 to 6.7 in the textbook on your own. Before you do that, make sure that you fully understand the solution of the example provided in this video. And with that, we have finished chapter 6. Thanks for watching, and I'll see you in the next video.